Okay, good. Hi everyone. It's Sunday, and this is part of the Thursday lecture. Sorry for the delay in getting it posted. As I hinted at on Piazza, ray tracing is going to be mentioned on the midterm. It's not a big part of the midterm. In fact, of the 30 points, only one of the 30 points involves ray tracing. But I wanted to just discuss it a little bit more. I know that I had the YouTube video from Walt Disney's Disney Corporation that I posted, but I just wanted to talk about it in a little bit more depth. And this will just be a few minutes, and then on Thursday's lecture, so on March 7th, I'll actually give a whole lecture on ray tracing that will be all of these slides. The thing that I really want to focus on right now is how ray tracing works. And the idea is that you'll have a viewer, and that's this eyeball right here, and you'll have a bunch of geometry. And then for every pixel in the image, you cast a ray from the eye to the center of that pixel, and then you see what you strike. And so in this case, if we were to follow this ray, through the image, then we would end up intersecting this red triangle in the front. And so the ray that goes from the camera through a pixel to some piece of geometry is called a primary ray. And if we were to just cast this so-called primary ray and calculate the color from the intersection of this ray intersecting that triangle, and of course one way to calculate the color would be to say it's red. Another way would be to do a lighting equation, take a normal of the triangle and then calculate the Phong shading as we did before. If we were to do that, then the picture we would get would be identical to rasterization. It turns out with ray tracing you do more than that. What you do is you start with the primary ray, and from the object through the center of a pixel, figure out what you hit, and then you then send out a large number of secondary rays. So as you hit this location, you then create more rays that emanate from that location, and you calculate what each of them see, and then take an average of the contributions from all the secondary rays, and that's the color you assign to the primary ray. I'm sorry, to the pixel on the screen. And so I'm going to talk more about this. What I'd really like you all to understand is just the computational complexity, which is you are casting, a million primary rays. Potentially, you have lots of secondary rays. And then for each of those rays, you need to figure out which triangle it intersects with. And so the worst strategy would be to say, here's a ray, and then I need to know which triangle it intersects with, and then to query each of the triangles one by one. Because you may have a million pixels and a million triangles, and if for each of the million pixels you consider each of the million triangles, you'd be doing a trillion calculations. So what you're better off doing is creating some sort of spatial search structure where you organize the triangles, and then for a given ray, you can ask what's the first triangle that this ray will hit, and that you can answer that question with a very low number of calculations. And so then the game plan is that you pay an upfront cost, ideally if there's n triangles, like an n log n cost to organize the triangles into a spatial search structure, and then for each of the rays that you cast, you only need to consult with maybe a constant number of triangles or a log n number of triangles, probably log n, to determine what the first triangle is that you hit. And so that's kind of ray tracing in a nutshell from a computational perspective. Again, one ray for every pixel, and then the work for that ray is ideally pretty small if you've put this into a spatial search structure. And then if you have secondary rays, well, then the work gets to be a lot more. although for each of those secondary rays where you have one ray hitting a location and then you have many more rays emanating out, then you also hopefully can accelerate the calculation of those secondary rays through the search structure. There's formulas for how to calculate these rays, and the formulas just involve some math, and so the amount of work to calculate any given ray is constant. It comes down to figuring out what the first triangle is that a ray hits. I also realize I've done a bad job giving credit for this. This is my second take of this video. The first time I did it, I did a better job acknowledging that I got these slides from, and I'm not very good at saying Chinese names, Xiaoyu Zhang from Cal State San Marcos. And so I'm reusing some of those slides. In terms of this issue of secondary rays, some of the images that you'll see that are kind of the old reference images for ray tracing, you can see that, for example, a ray came and hit the counter, and then as it hit the counter, other secondary rays were cast out, and then that's what allows you to see the reflection of the teapot on the counter, or shadows, or the reflection of the teapot on the tile. There's a ray hitting from my eye to this spot here on the tile, and then secondary rays come out and are bouncing from the tile onto the teapot, and that's why we're getting a color for this tile that reflects the color of the teapot at the mirror image location. And in this case, the tiles would have had different colors, and so then the background colors and actually the orientation of the tiles are impacting the reflection that we see there. This model is really focusing on a small number of reflection rays. If you want to get images that look really beautiful, then you actually cast a very large number of reflection rays. And so this would be an example of a very large number of reflection rays. This was made by Intel using their Embry ray tracing software. And so you can see there's very soft shadows here, and so that's because they cast so many secondary rays, they get these beautiful average effects that look like what we'd see in real life. So I think that's enough. We're going to discuss this more on Thursday, and for the question on the midterm on Tuesday, I think that it will involve mostly rasterization, but a little bit about ray tracing, understanding computational complexity. And so I think what we've discussed in this video is enough for people to feel like they can really succeed on the question. Okay, that's it. I'll see you all on Tuesday. Bye, everyone.